don't need to factor it in. And so if we're going to use this idea, then we're going to say, okay, well, P at 1, which is the gauge pressure at the inlet, divided by rho water, because it's water, right? And then you add that to the velocity at 1, so that's going to be 1.2 meters per second squared. Divide by 2 times 9.81, right? And then add that to, and then don't add anything actually, because remember it goes to 0. And then you say that that's equal to P ATM divided by this plus the velocity v2 squared over 2g, and g is 9.81. And by the way, this is the reason why we're going to use the continuity equation, because we don't know. But if we did, then we would be able to figure out what P1 is just by simple, just rearranging of the equation. I'm not going to rearrange it once we get V2, but this is 9. Remember, this is 9810 newtons per meter cubed. Don't forget that. And so, if we're going to do this, we're going to need to know. We're going to have to now use the continuity equation. So the continuity equation, well, let me go back to this first of all. So that's PATM, and the gauge pressure has to do with the absolute pressure minus the PATM. So let's just figure that out later. But for continuity, what we have is V1A1 is equal to V2A2, and so V1 is 1.2 meters per second. A1 is pi times. And then this is, they give the diameter, so we'll just have it really fast. So that's 75 millimeters squared is going to be equal to V2. So V2, which we are trying to find, times pi times the diameter divided by 2 is 37.5 millimeters squared. So then that just gets us our V2. So that's V2 is equal to... the pi's cancel, and then we get 1.2 times 75 squared, over 37.5. And by the way, these do not need to be converted to millimeters because the millimeters cancel out. So you could just say the millimeter cancel out. And we're going to go ahead and compute that. That's divided by 35 squared, 75 squared divided by 37.5 squared, so that's 4 times 1.2, and this is 4.8 meters per second, and that's what this is. That's 4.8 meters per second, and then we can just get to solve for P1. So P1 is it's kind of weird because let me just rearrange everything. So I don't know. So if we have 1.2 squared divided by 2 divided by 9.81, and we get 4.8 squared divided by 2 divided by 9.81. And what we get is that PATM, and we have plus 1.1 times the gamma W is going to be, whatever that is. But remember, it's asking us the question such that PATM doesn't, such that it's just the gauge pressure. So gauge is obviously just this portion, and so what we have is 1.1 times 98. Well, so this is going to be this. So this is PA gauge. So that's about this, right? And that will be our answer. Thanks for watching. We're going to go on to the next problem. By the way, so chapter 8 continued. Let me So yeah, the next thing that I wanted to talk about are the general ways that you compute HL, and in the FE it actually gives it in the HF form. So HF in or HL, whatever you want to call it, is generally based upon a very or just evidence slash empiricism. So, but for the Darcy-Weisbach equation, don't know where it comes from. I just know that it's very commonly used to figure out what the head loss is. So if we know what the length of the pipe that we have, or whatever is creating the friction, the boundary, and we know what the diameter of that is, and we know what the velocity is of the flow, and obviously everyone knows what G is. And then if you're able to find out what F is from the Moody diagram or some kind of other diagram, then you can find out what your head loss is. So it's basically a matter of sort of bookkeeping, and it can take a long time to establish all the variables, especially the F factor. But it's not that hard, especially for the FE. The FE, it's really simple. So why don't we go ahead and move on? And so F is the most important, probably the most important variable here. F is the most important variable for HL. Let's focus on it. So, although we can say everything else, right, this is called the friction factor, and it's the most important thing. And you'll agree pretty soon. So, first of all, let me review what the Reynolds number is. The Reynolds number, remember, it was V. Earlier, I wrote out that it was VD over the kinematic viscosity, and there's a reason why the kinematic viscosity is very important, because when you get the Reynolds number, you can determine not only if it's laminar flow or if it's turbulent flow, but the information related to turbulent or laminar flow is mostly important for determining friction factors, including the friction factor itself. So let's say, because when we can get the Reynolds number, it allows us to determine whether it's laminar in the case of Reynolds number being less than 2,100, and fully turbulent for greater than 10,000, and transitional for between 2,100 and 10,000. So, but why is that important? Well, it's because if we were to know whether it's laminar or not, it allows us to to simplify things. So, okay, so I might have misrepresented my the boundaries a little bit earlier, but basically the idea is that if you're in this zone, then you're able to use this equation. Now, technically, there's a critical zone, but during the critical, for the critical Reynolds number, you sort of cap out. So the critical zone, it's sort of a special case. So don't really worry too much about it, but just realize that if you're in the critical zone, that you just take it as where it was at the critical. So or whatever it is, they should give you the critical Reynolds number, and whatever that is, take the friction factor later than that as being 64 over RE critical. So that's all you have to know for that. But in general, for both the RE between 2,100 and 10,000 and RE greater than 10,000, you would have to find the F factor through these charts, and it's not just a simple formula. So you could say that in these cases, F requires direct chart reference. So we could say this is case 2. And then this is case 1. And case 1 is to be taken lightly in the sense that if RE is greater than the critical, then you take F to be at critical. So anyway, let's go ahead and move on. So chapter 8 continued. Pressure drop for laminar flow. The equation H in terms of the pressure drop delta P is the Hagen-Poiseuille equation. This relation is valid only for flow in the laminar region. So remember what that means. Remember what flow in the laminar region is. It means that what we need to do is figure out is that we would need to require that RE is less than 2,100. And the calculation for RE, remember what RE is. RE is, never forget, try to not forget, is the velocity times the diameter divided by of the flow divided by the at some point divided by the and the velocity I think is taken as the average divided by the kinematic viscosity. Let's move on. And so this equation is important. Why? Because this is a general way to get the discharge if you know what the pressure drop is, and we'll see a problem like that soon enough. And notice how it uses the dynamic viscosity. That's somewhat important to note. Anyway, let's move on. And so similarly for problems that involve this equation, such as when you're using the circular tubes, you would just use this equation if you're interested in the velocity. Hold on, let me go back. Yeah, anyway, so if you're going to use it for the velocity, so and that might be important. And then Vmax lets you know what it should be, because sometimes you might be concerned and say, well, what is Vmax, right? It's going to be, it all depends on the type, if it's turbulent flow, laminar flow, and so on. So you can go ahead and use this, information if you're not given it. And obviously this is the average, so velocity. So if you need to find what V of R is, I would use the maximum, this data for that, and you should be able to figure out what it is. So for example, for a parallel plates, it's going to be 1.5 times the average velocity, and then in general it would be the velocity at the center line of the duct, so which isn't necessarily obvious, right? So just use this information if you need it. Okay. So, and it's not just for circular tubes, it's also for plates or planes. So you can get pretty creative with this. Anyways, let's move on. So now for this type of problem, what you're going to see is the pipeline problem kind of extends from the other concept, because when you're trying to determine what the head loss is, you're going to be using the Darcy-Weisbach equations, but you could also be more practical and say, well, what if I have something where I'm given data, right, and you want to know something about pipes, you might say HL1, HL2, HL3, and you want to know if you already know what HL1 and HL3 are, but you're not given any other information, and you want to know what this is. Well, it's pretty simple, right? Because in general, for each mesh, this is going to be equal to 0, right? Because and it may not be obvious to you, but if you end up with a multiple pipeline problem, then you might actually be asked to do something like this, where you would have to use your knowledge of head loss addition. So in this case, whenever you're given information about this, even though you don't know anything about, even though you might know a lot about parallel pipes and series pipes, when in doubt, you can always use this type of equation. And this is somewhat of a hidden equation because they're not going to, it's not provided in any of my review stuff, but I just know it from electrical circuits. It just so happens to be applied to pipes. So if you think of the head loss in a pipe as if it's lying in a plane and not affected by gravity, in other words, the elevation is the same throughout the pipe, then what you could do is you could take a mesh through each portion of the pipes, and sum up each head loss in that mesh to get 0, so you could solve for the head loss in another part in another pipe if you know the other head losses. So, and that's kind of a practical thing, because in general in here what we see is that they're parallel, right? Which means that for a given parallel pipes, you have that the HL is the same. And then but then you're going to say Q is different. But then for a set of series pipes, Q is same, but HL is different. And that's how we can generalize this type of understanding. So, in other words, so then if you were to do something like this, these are neither in parallel nor series. This is a delta connection. So if you were to find, if you were given, say, HL2 and HL3, then it would just be as simple as HL1 is equal to HL, 2 plus HL3, and you could say minus. Because if you were to add them all up, assuming that they're all in the same direction. Now this, you have to have some judgment here, because sometimes it may not be, depending upon the flow rate. So if these were all in the same direction, then this would be the case. But you have to have your own judgment. In other words, the most important thing to remember is that HL of the mesh, the sum of the HL of the mesh in the mesh is 0. And that is not, this is important, but not covered by Lindeburg. So hopefully you can see that being the case. Now, as far as these equations go, they're just the Darcy-Weisbach equation. And as far as this goes, it's kind of the same thing. But let me just sort of peruse what this means. So this, let's see. So it looks to me like it's the area. So obviously this is just the continuity equation in a different way, right? Because this is just continuity. Because if we were to look at it like this, where you have pipe, a pipe going this way, and then a pipe going that way, then you basically have this thing going on, and basically because it's the same area. I mean, it's the same fluid throughout. Then we could basically say, okay, well, there's a velocity here, and a velocity here. So if you were to take the AV here and then AV here, they're going to be equal to each other. And that's what that is. So, and really, obviously, you want to make a judgment call, so this is the sum of the AVs, right? Another way of stating this is basically the fact that it has to do with control volumes, but I'm not going to go into that too much right now. I might go over it a little bit later, but for now we can look at this as if it's a continuity equation. So, and it's the same thing. I'm not going to derive it because it's going to take too long. Let me move on. So let's see an example. To measure low flow rates of air, a laminar flow meter is used. And remember, let's go back, because specifically this can apply to any fluid, not just liquids. So let's see how that applies here. So we say to measure flow rates of air, a laminar flow meter is used. It consists of a large number of small diameter tubes in parallel. So keep that in mind, parallel. What does that mean? It means that all the discharges across each tube is the same. One design uses 4,000 tubes. So that actually means that we're going to have to get the overall charge through all of them discharge, you're going to have to add them all up. So, I'm sorry. I meant to say that basically you have that because they're parallel, the HL is the same, but Q is different. So, which is why you would want to add them all up, right? So what we have here is that's the case. So then it says one design uses 4,000 tubes with each with an inside diameter of 2 millimeters and a length of 25 centimeters. The pressure difference through a flow meter is 0.5 kPa, and the absolute viscosity of the air is whatever. The flow rate of atmospheric air is at 20 degrees Celsius is most nearly what? So when they're saying flow rate, right, they're asking for Q. And so we don't know what that is. But we do know that Q is going to be the sum of all Q's given by HLI. So I equals 1 to 4,000. And so, but because they're all the same, these are all the same, right? All same. Then we know that this is just obviously 4,000 times QHLI. Because they're the same diameters, right? You have 4,000 tubes, same diameter, same length. So what we're going to do is we're going to have to find out what QHLI is. So let's go and see what we can do from the equation. So we could use this equation, right? Because we're given what R is, we're given what the change in the difference, the pressure difference, and we're also given the dynamic viscosity, right? Or are we not given? It says the absolute viscosity. Oh, we're given the absolute viscosity. So, I think that also implies the dynamic viscosity because it doesn't say. Although it doesn't say, implies the dynamic. So we're okay with that. But anyway, so basically, and we're also given the radius or diameter, and we can find the radius easily, and the length. So we can use this equation, and I'm sorry to sort of leave you in the dark here, but basically, because the page number I used here is for, the handbook is what's the page number I used? So the page number I used is this one is I used page 106, but basically everything is important for fluid mechanics, so if that's readable, please. Okay, 106. So I used page 106 for all these equations. Anyway, which may not be obvious to you. So if we use this equation, then basically Q is going to be pi r cubed to the fourth delta PF divided by 8 mu L. And so, this one seems kind of questionable, but I think we're just going to go ahead and use it. It says absolute viscosity. I think they still mean, dynamic, but yeah, so let's go ahead and compute that. That's going to be pi times the radius, 1 millimeter to the fourth, times 0.5 kPa divided by 8 times 1.81 e to the minus 8, and then further it's kPa, so k, we'll just say k, and then you have the length, which is 25 centimeters. So that's going to be let's see. it's going to be 0.123443339, and then that's discharges in meters cubed per second. So if we multiply, so if we take Q, it's going to be 4,000. Remember, it's 4,000 times this number. So then that's just 0.174 meters cubed per second, and that's about B. I mean, and that's pretty much the answer. So we're going to move on. Anyway, let's move on. So, continued flow in quantitative instruments. So, in general, for flow in quantitative instruments, you're basically saying, okay, well, I want to get an idea of how much this is flowing, or perhaps you want to know what, because a pitta tube, what a pitta tube will do is it will give you a measure reading in which you can then find what the full velocity is very easily, and that will give a good approximation. So as you can see from Bernoulli equation, you can actually obtain what this is, and we won't go over it, but this is very important, and you will see that, and all that means is that if you're given the head from the instrument, then all you have to do is just, if you want to find out what the velocity is just say, okay, well, I'm going to just multiply by 2g by the head and square root it to find out how much I have, or what the velocity of the flow is at that point. And you could do this very experimentally, and you can, and basically this is what you're doing all the time until you get it. And then you might have other instruments such as a Venturi meter. Venturi meter is basically where you have a smooth transition in between. So you might have something going on, like you might have a static device, and then here you're gonna do something strange, like you might have something strange like where basically, I don't know, your static tube is here, and then it just flows very evenly here, and and so I don't know, something like that. And this is poorly drawn, but it's something like that where you then get a reading in between, and then this is basically it. So yeah, I mean, basically when you're determining everything, you're just using these equations, this equation, and it'll tell you what the flow rate is here, and so on. So this is very poorly drawn, but just know to use this equation, because basically I think the whole equation is this one. I'm sorry. But it's pretty complicated, but basically what it is it's like if you have a P1 here and then a P2 over here, something like that. We'll see a little bit later. So P1, it says, yeah, so we'll see it a little bit later, but it's very simple when you use it. So let's not think of it right now. We'll just move on. So now with orifices, you want to pay attention to what the C is, the coefficient, because it can vary. For example, the coefficient in both of these cases is going to be used in the same way. So in this case, for these types of problems where it's sort of like it's submerged, and then this one's discharging, the C is clearly the product of CC and CV. So in these two cases, it's CC times CV. But in this case, it's a lot different because CC is CV times CC over the square root of 1 minus CC squared times 1 naught over A1 squared. So it's different. So in this case, CC is just simply the product over here. And then in the case of an orifice where it looks like a pipe, you just use this as C, as your C. So, and the reason why this is important is because the C that you use over here is going to be used in this equation. And the C that you use over here is going to be used in this equation, and the C you use over here is going to be used in this equation. So it all depends on what's going on, but I would familiarize myself with the particular C that you're going to be using. So let me go back to this because I think this also had its own sort of idiosyncrasy. It looks to me like there's no C in here, just CV. So in this case, you kind of just use the equation. And I'm sorry if I didn't go into too much detail on this. I'm just trying to get through it. But it looks something like this, where P1 is kind of like at one point, and then P2 is at the other. And yeah, so please go back and review that. I just can't go into too much detail for now. Anyway, so yeah, hopefully that makes sense, but I'm glad that I reviewed this. So the next thing we want to do is kind of see an application. So, or I guess we won't see necessarily an application, but all you have to do is remember that, and you should be able to get the equations right. So let's go ahead and move on.
Okay, so Chapter 8 continued. So with Chapter 8 continued, what we're looking at is the impulse momentum equation, which is basically, the momentum equation has a lot to do with the way in which you have a control volume and you can assume certain things about it. So in many cases, if we look at a control volume, then we can assume that it doesn't, that Eulerian reference frame, it does not change. So although it's moving, the fluid might be moving, it doesn't change, and thus this tends to go to 0. So like you might have this going to 0 for a Eulerian that's fixed. So basically what that means is that if we draw a control volume for, some kind of surface, then you basically have the sum of the forces been in a particular direction being equal to 0. So you might have something like like a pipe. In which case it might be like this, where it extends like that, and then the Eulerian reference frame is fixed. Then basically we can isolate it. We can say, isolate. We call this V1, V2, V3. So in this case, what you're going to have is that the impulse, based on the impulse momentum principle, what you're going to have is that the sum of the force in the x is going to be equal to, basically, like, let's pretend that, can I get rid of that? That the angle that this velocity vector makes with the horizontal is beta, and we're just given it. And then this angle with the horizontal is alpha, right? So then in the sum of the forces in the x direction is going to be, and then you're going to add, or you're going to subtract, because it has to do with adding vectors and stuff like that. So technically the force on the left is actually a minus, because the area vector is pointing to the left. So we'll put the minus, the area that's trying to go out. So that's the velocity is going against it, so it's going to be a minus. Here it's going with it because the area is pointing with the velocity here and as well as here. So the area vectors at those locations. So we're going to add that to V2, Q2, Q2, rho 2. But then remember, cosine beta, right? And then plus V3 Q3 rho 3 cosine of alpha. And so, you know, and then you also have that the sum of the force in the y direction is very similar. I mean, it's just going to be basic statics at this point, pretty much. It's not even dynamics, really. To a certain extent, it's not dynamics. The conclusion is the process to get to the conclusion is dynamics, but the conclusion itself is statics. So we have this here where it's sine of beta, and then you add that to, or really it's minus because the vector is pointing down, basically, you know, with respect to x and y. So we could just say, I didn't write it down, but this is x and this is y. So this is V3Q rho 3 sine of alpha. And then, so in many applications, what tends to happen is rho 1 equals rho 2, which is equal to rho 3. And you tend to just, because, you know, why would you have different densities based on continuity, right? So then they tend to go away. So, because this is 0, right? This is 0, based on the Eulerian reference frame that's fixed. And we don't have to go too much into that, but we could just assume that it's like if we were to take a control volume itself, that itself is not accelerating. Or I should say it's not moving. So we don't have to worry about it. And so then that would go away. And I'm not trying to do any calculations right now. I'm just showing you conceptually how this is. So this is the control volume. You know, trying to show you conceptually how this works because this is somewhat of an abstract idea. It's a little bit odd because normally when you think of statics and dynamics, you think of how rigid bodies move and not continuous things deform and stuff. That's just kind of strange. Anyway, let's move on. So we're going to see an example of this, and you'll see why I wanted to go over that in depth. So what you're going to see here is that if we're going to use that same concept, we basically have a you could think of it as a nozzle thing with air. It's supposed to be air. It looks like water or liquid of some sort, but it's just air that's pushing on the disc so that the disc can float in some way. It's a very strange apparatus, but I'll just read the problem. A thin metal disc of mass 0.01 kilograms is kept balanced by a jet of air. And so kept balanced basically just means it's being suspended. And so the diameter of the jet at the nozzle exit is 5 millimeters. Assuming atmospheric pressure conditions at 101.3 kPa and 20 degrees Celsius, the velocity of the jet as it leaves the nozzle is most nearly, and then they have some choices. So the way to approach this problem is just like the control volume idea. What you do is you take, because they assume that this is, they give you information about the nozzle, or you're trying to find something at the nozzle exit, which is here. This is the nozzle exit. You want to know, basically, you want to know what the velocity is there. So if we think of our control volume as such, then we can sort of say this is the control volume here. So body diagram. So this is just another way of saying just a fancy way free body diagram. So because of that, what we have is actually something that might be non-intuitive, which is the weight of the disk here, and we also have a couple of forces, or a few forces. Well, they're not forces, but we could just view them as velocities that contribute to forces. So we have some velocities there. These turn out to not be relevant, so we won't do anything. And you can sort of see why. Because if we think of this as our control volume or our free body diagram, then the only information we're going to need is something related to the things that are in the same direction. And you can see here that if this is V and it contributes to force, then the only thing that we're going to be required is the weight and a relationship here. There's another thing that we might want to consider, which is the weight of the air, but it's always so small that it doesn't matter. We could just say, but if this were water, we might want to actually consider this is W of air, which is approximately 0. So we're not going to care too much about it. So we're gonna go ahead and do the problem. And so from our momentum equation, we know that the sum of the forces in the y is equal to 0, which means if we assume a fixed Eulerian reference frame, which means that we know, that's just W disk minus Q times V times, from our equations, right, times rho. And remember, this is the equation. If you go back, that's the equation. Q rho V, right? So that's what I have here. We know that's going to be 0. And thus, because we want the velocity, right, then it's just simply W disk. Q, obviously, well, it's not so obvious to some people, but it should be V times A. We should know that by now. So it's going to be arranged so that W of disk, which is the weight, right, is going to be V squared A rho of air. And so this is the area of the location right here at the nozzle. So I could just say this is at nozzle exit. So what we have here is that this is V squared A, rho air, and this might be somewhat of a problem because we may not know what the density of air is, but which is typically sort of strange to get, but we can still work with it. Basically, if you want to get it, it's somewhat something that you're probably not going to see on the civil exam, but I'll just go over it. So we're just going to rearrange to get V. So V is equal to, if you could tell from basic math, it's just, we know this is M of disk times G, right? So basic math just says that this is the square root of M disk times G divided by A rho air, right? So let's just keep this here for now, and we're going to solve for everything because we need the area and everything like that. So we're going to get that the rho of air, and this is going to blow everyone's mind because they're going to say, what? It's basically P over RT. And this comes from, and it's ridiculous, it comes from, so this is going to be 101 or 0.3 kPa divided by, and I think this is 8, this is the 8 version, 3.14 times, what do we have, 20 degrees. This is the time where you want to use the units section just to make sure that you're good. So actually this should be kelvins, sorry about that. So kelvins is obviously you want to make sure it's 0 at minus. So this is, and oh god, 273.15 plus 20 kelvins. So, okay, I made a mistake with the value of R. The value of R, I made a mistake in the value of R, and it should be something else, because when we're using this version of the gas law, we're actually accounting for the fact that it's got a particular proportion with respect to its molecular weight. So if that's the case, then I'm using page 97 to get that it's actually 0.2870, and this is R, which is not the gas law constant, because in this version we have units of kj. Not only do we have units of kj per kilograms Kelvin, but this version uses rho air equal times RT equals P. But then this version uses PV equals nRT. See how they're different? Not just notationally, but they're different. So this is the real one, and I'm going to delete this. So what we actually should get is, by the way, this is information I was able to extract from page 73. It's in the thermodynamics page, which kind of sucks because you don't go over that in civil, but it's just the way it is. So yeah, keep that in mind, and we're getting an answer of 1.204 kilogram per meter cubed. So that's obviously what this is. And if we go through everything, it should be 64 meters per second. So that's about B, and that's the correct answer. So let's move on. Let me erase all this. Let's go to the next problem. And so now I wanted to do this problem because I wanted to show you that it's actually very easy just to use the discharge formulas that are given. So we don't need to do any Bernoulli derivation here. It's just a matter of using formulas. So it says a sharp-edged orifice with a 50 millimeter diameter opening in the vertical side of a large tank discharges under a I think it says head of 5 meters. The coefficient of contraction is 0.62 and the coefficient of velocity is 0.98. So let's go back to what the equation says. So what does the equation say? Clearly it's this type of situation that we have for I think it was problem 8.2. 8.2. So for this type of problem, we see that the equation that we're going to use is Q equals C times A naught times the square root of 2gh, right? Where h is the head, and this is clearly what's going on. So if we're going to see what C is, C, remember, what was C again? Well, if we go back to what it says in this description, it says, in which the product of CC and CV is defined as the coefficient of discharge of the orifice. So that means that C is equal to CV times CC, right? And although it doesn't say, well, it says it here. It says the coefficient of contraction. So clearly, this is, they're talking about this. So this is the coefficient of contraction. And then, so we can infer then that this is probably called the coefficient of velocity, because I'm not trying to, because I listed basically all the unique discharge formulas that we saw in the, that we see in the handbook, and so this is probably it. So if we kind of just think of in our heads that Q is equal to C times A naught times the square root of 2gh, then we could just solve using that equation. So it's just as simple as Q is equal to C A naught. Simple. This is how it's going to be on the exam. Very likely, this is what it's going to be like. And yeah, I mean, it's just, obviously it means that CV was, from our interpretation, we have the coefficient of contraction and the coefficient of velocity. We see that should be 0.98, and then CC is going to be 0.62. So, that's just why that I put that there. And then, so then A naught is just, well, that's whatever we see here, which is pi times, if you feel ambiguous, it's basically just this. So, 1/4, the basic area of a circle. And then times square root of 2, 9.81. Everybody should know 9.81. And then height is 5 meters. So you do everything and obviously convert millimeters to meters. And so what do you get? Well, let's see. You get, and by the way, for the problems that are kind of easy, they try to make the FE people try to make the answers kind of close to each other. So let's just see that we got to make sure that this is the as close as possible. So it should be D, but it could also be C. But I would say probably is D because we accurately laid everything out. So actually, D is the correct answer. So why don't we move on? Actually, I think that was the last problem. Thanks for watching. And by the way, this is another image of Pierluigi Nervi for more inspirational imagery. And yeah, I mean, congratulations on finishing this video if you had the volition to do so. It's probably going to turn out to be about 2 to 3 hours long. I still have to edit it a little. And yeah, I mean, if you watch this video, you're pretty ahead. And on top of that, if you would like, you can contact me on Praxi and for more help. So usually, and by the way, nobody's contacted me yet on Praxi, but it's a very new app designed for people to get very easy access to for almost practically no charge at all, to help them fix things in their life. So it could be repairs in the home. So you basically go on a webcam, and the other person will try to direct you on how to fix whatever you need to be fixed, and there's a particular charge per minute, and there's a minimum charge as well, and that just depends on who you are. But for me, it's at the very bare minimum. So so if you want, you can contact me at Praxi, and I can help you more on the FE or anything else, GRE. Could even be your own undergrad curriculum. It could be anything like that. I tend to be pretty available throughout the day because I am still looking for a job. I've been 5 months out of school, and I just passed the FE, and I'm really happy that I did, because then I can it opens doors to more opportunities. But I'm still in that process, and it's been pretty long. And as you can see, this is another thing that I'm releasing, in which hopefully somebody will catch on to my endeavors. So although I must say that this is for educational purposes only. It's not meant to gain profit, but please, I hope if you like this video, please subscribe to me and like this video, and then share it with other people who feel that they can they can use this for help. So it's a long video, but let me know. This is just section 1, so let me know if you want me to release more, because it takes a long time to put these videos together. So thank you very much. And we see another picture of Luigi Nervi, and he's a structural engineer from I think it's from the 50s. But again, he did a lot of structures for the aircraft, and then it turns out those projects were actually decimated and destroyed. So a lot of them were. So it's a little bit sucks a little bit, but he contributed to the basically the mesh reinforced mesh concept, which is a little bit odd to some people because it's essentially turning something that has moment into something with more axial action, and that is kind of a little bit strange. But he was able to basically create a, I think it was as small as 0.5 inches, the thickness of a of a boat. Basically, if you could do that, it's with mesh material, that has to have some value to it. And obviously that was innovative at the time. It still can be considered innovative. It's just people don't want to necessarily broaden their horizons. Sort of architects are into that, but we'll probably see more innovations later on. So thank you for watching. Yeah, so basically it was a hull. He was able to construct and design a hull that was less than 0.5 inches thick with reinforced mesh concept. So hopefully you like this video. Please subscribe and contact me on. Don't forget to sign up for Praxi and contact me on Praxi. The username is RD Flores. Thank you for watching.